Very good. It's 6 o'clock sharp, so let's actually get started. So welcome everybody to the session on quantum many-body systems. We have quite a number, 10 in fact, of interesting short talks coming up. We'll try to stick to the schedule as much as possible. And so in particular, since we have a talk every 15 minutes, I would like to ask all the speakers to take a maximum of 12 minutes for their talk. I will give you a 2-minute warning before the end, so that we still have a chance to have questions, 1 or 2 questions, and probably takes another minute or so to switch slides. So I will ask everybody to please stick to the schedule. So let's get started right away. I'm happy to announce Giulia Basti as our first speaker, and she will talk about a new second-order upper bound to the ground state energy of a dilute Bose gas. Please.
Thank you for the introduction, and thanks a lot for giving me the opportunity of giving this talk today. So it's a great pleasure. And I'm going to present a recent result obtained in collaboration with Serena Cenatiempo and Benjamin Schlein. And let me immediately start. Introducing the system of our interest. We consider M bosons in 3 dimensions confined in a box of side length L, and this HL is the Hamiltonian of our system. So we recognize the kinetic part where Xi is the position of the ith particle and then the interaction term, and we assume the interaction potential V to be positive, spherically symmetric, and compactly supported, and we assume Dirichlet boundary conditions. We are interested in considering the ground state energy per unit volume in the thermodynamic limit, which I denote with this E of rho. And let me recall that the thermodynamic limit means that we want to send both n and L to infinity, keeping anyway fixed the particle number, particle density rho. We want to find an expansion of this E of rho under the assumption of diluteness, meaning that we assume rho A cube to be small, where A is the scattering length, and in this slide I briefly recall the definition of scattering length. So let F be the solution of this zero energy scattering equation with the boundary condition that F goes to 1 at infinity. Then the scattering length A is just 1 over 8 pi, the integral of V times F. Then since F is always between 0 and 1, one can easily check that A is 8 pi A is much smaller than the integral of V, and this will have an effect later on. This scattering length is an important parameter, and in particular it is the only parameter which describes the interaction at low energy, and it has to be thought as the effective side length of the interaction. Let me also remind you an important concept, which is Bose-Einstein condensation. So it means that we expect that gas of bosons at low temperature in a dilute regime exhibit a macroscopic occupation of a single particle wave function, which is known as condensate wave function. Then the proof of Bose-Einstein condensation in the thermodynamic limit, it's certainly a challenging problem I definitely don't want to address, but it's important to keep this picture in mind in order to understand many things, many ideas that I'm going to present in a moment. And indeed, the first derivation of the so-called Lewisian formula, which is this expansion here for E of rho, was obtained by Bogolyubov, assuming Bose-Einstein condensation. The name Lewisian formula comes from this other paper, by Lewisian, and And both these papers were heuristic, and indeed the rigorous proof of this formula has been a long-standing problem, as you can see from the dates in the papers listed below. Let me just mention that when it comes to the second-order term, which is known as Lewisian correction, the upper bound was first proved by Yao and Yin in 2009 for regular potentials, while the matching lower bound was proved just last year by Fournet and Solovey for all potentials in L1. Now, again, we want to look at this Liouville correction, and we are interested in an upper bound. Let me now state the result more precisely. We assume V to be, again, non-negative, radially symmetric, and compactly supported. Moreover, we assume V to be in L3. Then we can prove this upper bound on E of rho in agreement with the Liouville formula. And as I said, an upper bound of this form was already available in the literature, the one by Yao and Yin. So let me briefly mention which are the main differences between our result and their results. First of all, we can handle a much wider class of potentials. Indeed, we don't need to ask regularity of the potential. Moreover, we provide a better estimate on the error, this 5/2 plus 1/10. And let me also mention that we could push a bit our method in order to reach the estimate rho power 5/2 plus 2/9. Anyway, we refrain from carrying out this more refined analysis because we believe that the main advantage of our method is that it is substantially simpler. Okay, I would like to spend the time left giving you the main ideas in the proof. First of all, let me mention that we are not going to prove the result directly in the thermodynamic limit. What we are going to do is to provide a trial state in a box, which side length I denote with this L of rho, and it depends on rho. Is defined as rho power minus gamma, and this gamma has to be larger than 1. Moreover, on this box, we consider periodic boundary condition. And once we have a trial state on this box, the idea is that we can easily modify it a bit in order to get a trial state on a slightly bigger box, now with Dirichlet boundary condition. And the advantage is that once we have Dirichlet boundary conditions, we can replicate this trial state in order to get a trial state on a large box made of T-cube copies of this light orange box separated by corridors of side length R, so that particles in different boxes, they do not interact. And now when T runs over natural numbers and goes to infinity, we are building a sequence of trial states with more and more particles on larger and larger boxes where the density is kept fixed. Namely, we recover the thermodynamic limit. Let me also mention that to simplify the analysis, we prefer to work in the grand canonical setting. And anyway, since we are in the thermodynamic limit, one can prove that a trial state in the grand canonical setting anyway provide an upper bound also for the canonical quantity E of rho. Okay, so this was very sketchy, but this strategy is very standard and was just to justify that from now on, we will focus on a box of side length L rho, changing with rho with periodic boundary conditions in the grand canonical setting. Now, just to be a bit more confusing, I prefer to rescale variables, reducing to the unitary box lambda, where we have to consider a rescaled Hamiltonian, which I have written in second quantization. So these AP star are just the canonical bosonic commutation, creation and annihilation operators, while the hat denote the Fourier transform, and lambda star is just the dual lattice of the box lambda. This parameter k is related with gamma appearing in the definition of L of rho, as you can see in the slide. And since we need, in order to apply the procedure I showed you in the previous slide, we need gamma to be larger than 1, we have to ask k to be between 1/2 and 2/3. And in particular, let me mention that k equals 2/3 would correspond to the thermodynamic limit. Okay, so the core of our paper is to provide a trial state in this new setting, which has the correct number of particles and has this, satisfies this upper bound on the energy. This is just the Liouville formula restated in this rescaled regime. Okay, so I now would like to show you how this trial state is made. First of all, since, as I said, we expect Bose-Einstein condensation, the first idea is to generate the condensate. To this end, we consider omega, the vacuum vector, and we act with this while operator W and 0 being a parameter I will specify later, but for the moment it can be thought to be just n, the number of particles. And the action of this while operator on creation and annihilation operators is explicit, but unfortunately, if we compute the energy of this trial state, then we immediately recognize, recalling the remark I made at the beginning, that the integral of V is much larger than 8 pi a, that already the leading order term we don't get it correctly. And the point is that in considering this trial state, we are just putting all particles in the condensate and we are neglecting correlations. So in order to lower the energy, we have to consider correlations. And to this end, we would like to take into account a Bogoliubov transformation of this form here, so the exponential of this operator. And of course, this is a unitary operator, and now it remains to specify the choice of this nu p. Since, as I said, we want to describe correlations, the idea is to consider the scattering equation. However, we are now working in the box, in the unitary box, so we have to modify a bit the equation. In particular, we consider this Neumann problem on a ball of radius L, and then omega L will be just 1 minus FL, and of course we have to consider a rescale version of the omega hat, the Fourier transform of omega L, because we are dealing with a rescale potential. Well, one can check that it's enough to consider these coefficients eta p on large momenta, and the idea is that we expect that these correlations only play a role on length of the order of the scattering length, and the point is that at the same time we would like to do something different on small momenta. More precisely, we consider the coefficients tau p defined by the equation on the bottom of the slide, and if one is familiar with Bogoliubov approximation, this is just the kernel which is needed to diagonalize Bogoliubov quadratic Hamiltonian. So to summarize, we split into the set of momenta. So we consider on low momenta these coefficients tau p, and on the complement of p low, the coefficients given by the scattering equation, and this is the Bogoliubov transformation. Then the trial state we consider is obtained taking the vacuum, then acting with T, and then with the while operator. This is still not enough. We have to do something different, something more to describe correlations, considering the exponential of a cubic operator of this form here, where pH is a new set well separated from P low. Unfortunately, the exponential of a cubic operator is not easy to handle. There is no explicit expression for the action on creation and annihilation operators, and indeed we have to add some restrictions on momenta implemented by this operator theta RV. This is the explicit form of theta RV, and unfortunately I don't have time to convince you that the role of this theta RV is crucial. It simplifies a lot the analysis and makes computation much easier. Just to conclude, this is the form of our trial state, and note that we are not considering this exponential of 8 is not a unitary operator. This trial state has the correct number of particles and provides the desired upper bound on the energy. Just one remark to conclude. I want to stress that the idea of using the exponential of a cubic operators comes from the heuristic of Yao and Yin, but our implementation is very much inspired by the work in the Gross-Pitaevskii setting by Boccato, Brennecke, Cenatian-Schlein, the GP setting being, in our language, corresponds to k equals 0. The difference is that in Yao and Yin paper, they keep the exponential of the quadratic and cubic operator all together, but of course it's then difficult to handle such an operator. They need to truncate the exponential and add several cutoff. On the other hand, since we first act with the exponential of the cubic on the vacuum, all the cutoff can be put in the definition of A, and we don't need to truncate. On the other hand, in the GP setting, one doesn't need to use this theta operator and can take the unitary cubic operator, since there are global estimates to control the errors, which is not the case in this regime where k is larger than 1/2. Okay, this concludes my presentation. Thank you for your attention.
Thank you very much. Since we're already running over time, I propose we have to leave questions for later. I mean, you'll find Giulia around later in the next days. So thanks again. And we continue more or less right away as soon as the slides up. The next talk, and I apologize in advance for probably mispronouncing your name badly. So it's Dinh Thi Nguyen from Lyon, and he will talk about the blow-up profile of 2D focusing mixture Bose gases. Please go ahead.
Thank you for your introduction. And I would like to thank the organizer for giving me opportunity to speak here in ICMP. So today I'm talking about the blow-up profile of 2D focusing mixture Bose gas. The Bose-Einstein condensation with multiple species can display some interacting phenomena absent in the one component BEC, and the simplest multi-component BEC is the binary mixture. So in this talk, I will consider N1 plus N2 quantum boson in R2, consisting of two different families of N1 and N2 identical boson. So here I will consider the total number of particles is denoted by N, and the many-body quantum system contains two non-relativistic adjective system and interspecies interactions. So here the external potential V1 and V2 are drop-in potential, and in the laboratory experiment they are harmonic potential. The interspecies and interspecies interactions at Riesz scale two-body potential with the length scale n power beta for some beta non-negative, and the integral of the unscaled potential is denoted by I1, I2, and I1 to measure the interaction strength. And we will need further assumption on the unscaled potential in order to obtain the conversion of the energy. The coupling constant proportional to the choice of the coupling constant proportional to 1 over N1 minus 1, 1 over N2 minus 1, and 1 over N ensure that the kinetic energy and the potential energy are comparable in the Minkowski mixed regime n to infinity. And we will assume that the ratio N1 over N and N2 over N are fixed and between 0 and 1. This guarantees that the population of the two species are comparable. As usual, the Gross-Pitaevskii energy is defined by the lowest spectrum of Sn. Here the system is, so here we will assume that the interaction strength, all of the interaction strength are positive. So this corresponds to the case where the case of the totally adjective system. So here, for the particle in the same species, is it allowed to exchange the particle in the same species? It means that the wave function remains the same when we exchange to any particle in the same species. However, it is not allowed to exchange the particle in the different species, and this much different and difficult in order to compare the two component problem and one component problem. So the system here is adjective, so it's unstable. So the blow up might happen, And the goal here is to study the profile of the Gross-Pitaevskii energy per particle and the Gross-Pitaevskii when in a collapse regime when number of particles convert to infinity, and at the same time that the total interaction strength tend to a critical number I star, which I will describe later. So recently there are some results in this direction. So in one component setting, Gu and Seilinger studied the collapse of the NOS energy and Gross-Pitaevskii. Later, this result was extended to the many-body system by Lewin, Nam, and Rougier. So in order to prove the conversion of the Gross-Pitaevskii, they use the Fermat-Hermann argument, which rely on the uniqueness of the limiting profile and a quantitative energy estimate. So the latter is essentially followed from the argument of Lewin in his proceeding from ICMP 2015. So this will be also our tool in order to study the problem in two-component setting. So in this setting, the collapse of the NOS energy and its Gross-Pitaevskii was studied by Gu, Yen, and Zhu. So another result here is related to the critical number I star, which is the critical number in the Caledonian bus inequality. So in fact, we can calculate explicitly this number by the L2 num of the unit solution to the nonlinear Schrödinger equation. So let me remind you the result in the effective theory, because this is the first result in order to study the totally focusing mixed two-Bose gas. So in the nonlinear Schrödinger theory, Gu, Yen, and Zhu proved that when we fix the interspecies interactions and we choose the external potential of the form S power P, then in the collapse regime when the total interaction strength convert to the critical number I star, then the rescale of the NOS Gross-Pitaevskii convert to the unit Caledonian bus solution. And this follows from the asymptotic formula of the NOS energy. So the main result I want to talk today is as follows. So let beta between 0 and 1/2. So I remind you that the interaction potential are rescaled to body potential with the length scale n power beta. The external potential is of the form S power P. And when we fix the interspecies interactions, then let the total interaction strength tend to the critical number I star slowly. Then in this collapse regime, the rescale of the mixed two Gross-Pitaevskii is fully condensed on the unit Caledonian bus solution in terms of the reduced density matrices. And this conversion follows from the Fermat argument, which rely on the uniqueness of the limiting profile Q here, and the asymptotic formula of the Gross-Pitaevskii energy per particle, which is similar to the NOS energy. So here I remark that there are two conditions on the parameter gamma. So the first, the condition that gamma is smaller than B0 plus 2 over B0 times 1 minus 2 beta imply that we consider the mean field interaction. So this corresponds to the high density regime where the particles meet frequently but interact weakly. And the other condition that gamma is smaller than B0 plus 2 over B0 plus 3 times beta, we need this assumption in order to compare the NOS energy and the Hachi energy. So the Hachi energy is obtained by considering that in each species, we assume that all other particles are in the same quantum state. So this corresponds to the choice of the triostyle U1 tensor N1, tensor U2, tensor N2 for the Hamiltonian Sn. So let me spend a few minutes to tell you the ingredient of the proof of the theorems. So for the conversion of the energy, we first use the Hartmann-Ortenhop inequality to estimate the kinetic energy. And it can be done in each species. So the difficulty is to estimate the two-body interaction from below. So here we will use, this will be done by the Onsager lemma and achieved due to Lévy-Leplon. So Onsager lemma deal with the case when all other interactions, interspecies interaction and interspecies interaction have positive Fourier transform. And for the general cases, we will split the two-body interaction into two parts, and both of them have positive Fourier transform. And then we can use the Onsager lemma to estimate the Gross-Pitaevskii energy per particle from below by the Hg energy of the square root of 1, 0, and 0, 1, then particle density. And the price to buy in this, process is n power 2 beta minus 1. And of course, the Hg energy is an upper power to the Gross-Pitaevskii energy per particle. So next, in the stable regime and with further assumption on the unscaled potential, we can estimate the NOS energy and the Hg energy with an error term is n power minus beta. So it is very natural to require that beta between 0 and 1/2 in order to obtain a conversion of the Gross-Pitaevskii energy per particle to the NOS energy. So with the quantitative energy estimate, now we can use the Fermi-Liquid argument to obtain the conversion of the Gross-Pitaevskii. So the fact that the conversion of the generalist KL particle density matrices follow from the conversion of the marginal 1, 0, and 0, 1 particle density matrices, and this was proved by Michelangeli and Ogiati. So in order to prove this, we will consider two perturbations in the group of N1 and N2 particles. With a small parameter epsilon, we will choose is equal to little o of ENOS. So now we will estimate the energy. So the thing here is the Hartmann-Ortenhop inequality is not available to estimate the kinetic energy, but the Onsager lemma is general, and we can still use it to estimate the Gross-Pitaevskii energy per particle from below by a Hg type energy divided on the Joyce-Glasser joy operator. And this is the case for the 1, 0, and 0, 1 particle density matrices. And by the adjectiveness of the interspecies interaction, we can estimate this energy from below by the modified Hg energy. And of course, the Hg energy is an upper power to the Gross-Pitaevskii energy per particle, and we can always estimate this energy with the modified Hg energy with an error term n power minus beta. So by using the Fermi-Liquid argument, we can, by using Fermi-Liquid argument with this energy estimate, we can reduce the conversion of the Gross-Pitaevskii to the conversion of the modified Hg Gross-Pitaevskii, and this is somehow similar to the NOS Gross-Pitaevskii. And this finishes my talk, and I would like to thank all of you for your attention.
Thank you very much. So again, I propose we leave questions for later in the interest of time, and we move on right away to the next talk. Niels? So we're still waiting for the slides. Oh, there they are. Okay, great. So the next talk is by Niels Benedikter. He's describing quantum correlations in the Fermi liquid by bosonization.
Okay, thanks. Unfortunately, I prepared my talk to be 13 minutes long, so I guess I'll just have to speak 7.6% faster now. Apologies for that. So this is about an ongoing project on the description of quantum correlations in the Fermi liquid by means of bosonization methods. And, well, what are we interested in? Well, roughly speaking, the behavior of electrons in a piece of metal. So mathematically, that would be, we're interested in the Hamilton operator of n spinless fermions on the fixed size 3D torus, as you see it up there written in blue. So there you have a kinetic energy with a Planck constant h bar. We have a pair interaction in terms of some multiplication operator v with the coupling constant lambda, and of course this acts on the L2 space of antisymmetric wave functions of 3n variables. Now, typical quantities of interest for us would be the spectrum, sigma of hn, and then in particular the ground state energy, that's the infimum of the spectrum, or equivalently the infimum of all expectation values of the Hamiltonian. And of course we should fix the physical regime of interest precisely, which for us would be a gas of very high density and with rather weak interactions, which we do by setting h bar as n to the minus 1/3, the coupling constant lambda as n inverse, and then considering the asymptotics as n to infinity. So that's what we call a mean field coupled to a semi-classical scaling limit, very similar to the one that also Chiara Zafirio presented. So, okay, so what is this bosonization? How do we define it? What do we want to achieve? I'll have to start with this preparatory slide, which is not yet bosonization, which just has the purpose of introducing a way of separating excitations from the or to phrase it like that, which has the purpose of describing our Fock space not in terms of excitations over the vacuum, but in terms of excitations over the non-interacting ground state. And that's by means of a particle-hole transformation. So we just write the Hamiltonian second quantization, as you're all used to. We introduce fermion equation and annihilation operators of the Fourier modes. So you get this expression up there that you also find in every physics textbook. And then we apply this particle-hole transformation. So what does this particle-hole transformation do? Well, it's defined with respect to the non-interacting Fermi ball. You see written BF is just the Fourier modes, the n Fourier modes of lowest kinetic energy. And then we say, well, a creation operator A star k is transformed into a creation operator A star k if you're outside the Fermi ball, nothing happens. If you're inside the Fermi ball, a creation operator is transformed into an annihilation operator. So you should really think of describing your quantum state as making particles on top of the Fermi ball or creating holes in the Fermi ball. And then you transform the Hamiltonian with that, and you find the form written in the last equation. You see, the nice thing is, as the first term, you already get the Hartree-Fock energy, which in this case is just the expectation value of the Hamiltonian in the non-interacting ground state. That's the E Hartree-Fock that you see there. Then you have the kinetic term, which for the particles just stays invariant, h bar squared p squared, and you get a kinetic term for the holes, which comes with a minus sign. This, I think, rather intuitive. And finally, you have a term q, which is just a transformed interaction, still quartic in creation and annihilation operators. Now, what do we want to do with that? Well, we want to find a quadratic approximation for this excitation Hamiltonian, h kinetic plus q. Quadratic because we like quadratic Hamiltonians always, because we can diagonalize them by means of a Bogolyubov transformation. Okay, so bosonization starts with a very simple observation, which is the observation explained here, namely if you introduce these pair operators, I wrote in blue, which is creating a particle of momentum p and creating a hole of momentum h with relative momentum fixed to be p minus h equal to k, and summed over all possibilities, then the interaction operator q takes a very simple form. It becomes quadratic in these operators, and you also find that these operators behave approximately as bosons, in the sense that a B star with a B star exactly commutes, whereas a B with a B star gives you a delta KL up to some normalization and an error operator E of K and L, which we think of as small. Okay, very nice about the interaction. What do we do with the kinetic energy? Well, we come back to an idea that emerged in the 90s, and there are far more references that I could fit on this slide on the use of this idea, which is that you take your Fermi ball, like the surface of the Fermi ball, you cut it up into these rectangular areas, which we call patches. The number of patches will later depend on the number of particles and tend to infinity. And well, then we localize these pair operators, right? You see the pair operators get an additional index alpha, which stands for the patch, and the p's and the h's, the momenta, get localized to living near such a patch, B alpha. The advantage of this linearization is now you can linearize the dispersion relation, then you can compute a little bit, and you find that a commutator of the kinetic energy Hamiltonian with a bosonic pair B star alpha k is 2h bar Euclidean product k omega alpha B star alpha k. And then you conclude with the observation that the same commutator can be obtained with the expression written up there in the very last line, namely this quadratic expression. Right, the U alpha k squared you see there is just an abbreviation for this Euclidean product k omega alpha. Okay, so back to the interaction for a moment. Of course, also there we have to do the decomposition into patches. It's very simple. The only thing that's a little bit less simple is you have to compute these normalization constants n alpha k. So it turns out they should be the number of particle hole pairs in patch B alpha with momentum k, relative momentum between particle and hole k. And with a little bit of number theory and some projection argument that is sketched in the graph up there, you find that this is, well, this 4 pi n to the 2/3 over m times again this geometric factor k Euclidean product omega alpha. So you plug all that into your Hamiltonian, and you get the expression written here in the last line. So that's nice for a couple of different reasons. First of all, it's quadratic. It's almost bosonic, as I tried to convince you already. And it has these nice coefficients U alpha, both in the kinetic part and in the interaction part. Those are quite important, actually, because the kinetic part of the Hamiltonian has a really tiny gap. So it's really hard to control the interaction just by the kinetic energy. But thanks to the fact that this U alpha appears as coefficient both in the kinetic part and in the interaction, if you think of a sort of perturbative expansion, right, you'd have interaction divided by kinetic energy everywhere, and these factors just drop out. So that sort of regularizes the whole problem for you, and that actually plays quite an important role. But that's maybe more common for the experts. Okay, so we have an effective Hamiltonian that's quadratic, that's bosonic if we forget about this error term E of K and L. So let's take that approximation serious and really drop this error term. Then we can diagonalize H effective by means of a Bogoliubov transformation. That's a computation you can find written up in that paper reference there, and it gives rise to this picture here I've sketched in these graphs. So on the very left, you see the case of no interaction. And you should think of what you see there as a continuum for the spectrum, right? The discrete resolution you see in the vertical direction is just because I put a finite number like m equal to 20 patches in Mathematica. Should think as m goes to infinity, that becomes a continuum. Now, if you switch on a Coulomb interaction, you get the picture in the middle, which is you get one single mode that emerges on top, which is called the plasmon, and physically represents a kind of collective oscillation of all electrons.
So 2 minutes.
Okay. And the rest of the spectrum really just becomes very weakly renormalized. And actually that you find quite nicely confirmed in experiment. You have some experimental data from sodium metal up there, which I think the agreement is really quite beautiful. Now you might say maybe, okay, doesn't sound so exciting. Almost all the spectrum is just weakly renormalized. I would like to advocate that this is actually really quite exciting because you have a very strong interaction in the system. So it's quite surprising that it does so little except for the emergence of the plasmon mode. I would like to say that this is maybe a hint of that we have a non-perturbative way of describing Fermi liquid behavior here, which is exactly that. A system of fermions can generally be very well approximated as non-interacting. Now, for the last moments, let me just show you what we can do rigorously. So here's the theorem. We have been mostly focusing on the ground state energy so far. In a series of 3 papers, we went from the upper bound to a lower bound under the assumption of weak potential, and then in the recent preprint, you see as the last item, we could prove the theorem as it stands here. So under the assumption of that the potential is repulsive in the sense that the Fourier transform is positive, and with this summability condition here, we can show that the ground state energy is given by the Hartree-Fock energy, which you saw before emerging from the particle-Hole transformation, which in that sense is trivial, plus an energy that is called the random phase approximation energy. As a maybe a little bit complicated formula, you should think this formula comes from the infimum of the spectrum of the effective Hamiltonian that you can diagonalize almost explicitly. And in fact, in physics, this formula goes back to the 50s. More recently, it has also been proved rigorously by Christiansen, Heinzel, and Nahm. And just as a very last comment, I want to say that this method, I believe, has also a lot of potential to go beyond the ground state energy, so there's a lot to be done there. I showed you the spectrum that would be to analyze ground state properties, dynamics as an example. In 2014, we were able to show that the many-body time evolution in the sense of reduced density matrices can be approximated by Hartree-Fock theory. Now, 7 years later, we were able to show that a stronger approximation in Fock space norm can be obtained by using this Bosonization ideas. And I'm going to spare you the details. The archive reference for the last theorem is up on the slides, and maybe I can still take a question or two.
Thank you very much. We would have a couple of minutes for questions. Jan, go ahead.
So you mentioned the RPA approximation is approximately the ground state energy of the quadratic Hamiltonian. Can you explain why it's approximately that and how far it is from the energy for the quadratic Hamiltonian that you had?
Sorry, I couldn't quite understand.
So the RPA energy that you wrote, you said it was approximately equal to the infimum of the quadratic Hamiltonian. Why is it approximately equal, and how close is approximately equal?
How close, I don't remember. It's a rather tiny error compared to the other errors. The main reason why it's not exactly that formula is because of this discretization you have by having a number m of patches. Only by sending m to infinity you recover that formula.
Thank you. Any further quick urgent question? Yes?
In the experimental curve, the band seems to merge with the continuum, whereas yours is tangent. Do you expect to be able to understand this difference if you include more corrections?
I think that's beyond the approximation we have here. I mean, first you should see the error bands of the experimental data on the very right are huge. But physically, the reason why they are so huge is because this collective mode acquires a finite lifetime due to some remainder interaction in the system, which makes it decay. And of course, that goes beyond the approximation we have. So I don't think we can predict that, but the picture is that as soon as the mode comes very close to the bulk of the spectrum, it will somehow dissolve and become unstable.
Very good. So let's thank Niels again. Okay, we'll move on. Our next speaker is here. Very good. So can we have the next slides, please? Yeah, very good. So our next speaker is Louis Garrigue, and he will talk about inverse potentials of one-body densities. Please go ahead.
I thank the organizing committee for letting me presenting my work here today. Sorry, yes. I'm postdoc at the École des Ponts in the team of Eric Cancès. So I will first present the setting of our problem. I'll present the problem and what was found in it. Then I will, sorry? Yes, 41. We'll be quick. Then I will present a theoretical resolution of the problem. And lastly, some numerical simulations and what we can learn from those simulations. So we are in a static setting. We think about electrons without spin. Our states are antisymmetric, normalized to 1. They are functions of RdN. We take fermions, but everything would work with bosons too. The Hamiltonian is the many-body 1 with interaction W and electric potentials V. The ground on excited state and ground on excited energies are given by the min-max problem. And the key denotes the excitation, so it's 0 for the ground states and greater than 1 for the other ones. Of course, the problem is way too complicated to be solved numerically. This is called the curse of dimensionality, so we have to find other approaches to this direct problem. I recall the spectrum, typical spectrum of such Hamiltonians, and we denote by V the set of potentials which are able to bind n particles in the case bound states. So they have to be deep enough. We don't know any simple characterization of this set. We just know that it is open and path connected. So pure states are can be represented by rank 1 projections, and mixed states are the convex hulls of those pure states. And Kiss eigen mixed states are mixed states which live in the eigenspaces corresponding to the Kiss energy. The one-body density is important in our problem. It's the marginal over n-1 particles. It's positive and integrates to n particles. So the goal of our problem is given such density, so a positive function integrating to the number of particles. We want to find some potential V such that there is a Kiss excited eigen state, psi curve V, which has a density equal to the target density. So if it exists, we call it the inverse potential. And for example, there is an illustration here for 3 particles and key equal to 2, so second excited states. Can you find some potential which has such eigenstates having the target density? The answer is yes, and this is one solution.
So why do we want to invert those potentials? This is important in density functional theory, which tries to find one-body effective models to describe the n-body systems. It is extensively used in condensed matter and quantum chemistry and everywhere in quantum physics, even in classical physics. The idea is to get rid of the interactions and map fully interacting systems, very complicated, which is described by such a ground state density rho. And we want to map it to a much simpler model, one-body model. And we will do so by the previous inversion. So we want to find this effective potential V, because from this new system, we can extract anything we want, excited state energies, excited states, and so any physical quantity for free numerically. So this gives us approximations for any physical quantity. The direct DFT map is the one from potentials to densities, the usual one, and we want to invert it. So the first question is it injective? Because if yes, this means that our inverse potential will be unique. It is the case for the ground state, and it's called it is the famous Hohenberg theorem. The second question is, does the image, is this map surjective, or does the image is dense in the set in the image space? This corresponds to the existence of the inverse potential, and the answer will depend on if we look at pure or mixed states. A mathematical question is the inverse problem well posed. And finally, we would like to get an algorithm to practically invert this map and find solutions. So mathematically, the problem is ill-posed. And this corresponds to the fact that the direct map is weak, strong, continuous. So if you take a sequence of potentials which converges weakly, then the corresponding ground state densities will converge strongly. So it's ill-posed. The problem is ill-posed because the inverse map is discontinuous for ground states, and topologically the image of the direct map is very small. So there are two different problems. You can look at it for pure states and look at it for mixed states. Of course, the set of densities coming from pure states is smaller than the set of densities coming from mixed states. So this will be easier to invert the map for mixed states. You are more likely to have the existence of an invert potential. The inverse problem was solved by Lib in the case of mixed states for ground states with an abstract theorem, using an abstract theorem. Then it was solved for classical systems at strictly positive temperature by Chayes Lib. And it was solved for quantum systems on lattices for mixed ground states. So what we want is to solve the problem for the quantum continuous case and for any excited state, and also for pure states. So trying to improve those results in several directions. And actually there is not much more time. I will be quick. So everything relies on the study of this functional, which is the Legendre transform of the energy with respect to the density, because potentials and densities are dual quantities. It is gauge invariant, concave for the ground states, and the big problem we have to consider in this study is the fact that the functional is not differentiable. This corresponds to the fact that the energy is not differentiable on a potential which have degenerate eigenspaces. So this statement says that it's equivalent to have a maximizer of the functional J, the dual functional, and to have the existence of a mixed state having a density with having a mixed state having the right targeted density. And also there is no local maximizer, so this is very pleasant numerically because the algorithm won't block in local maximizers. So by this statement, we know that we can just maximize this dual functional to solve our problem for mixed states. I won't talk about that. So yes, we want to know if there is a maximum. The functional is not coercive. We can find a simple counterexample to the coercivity when the potentials are in LP. Coercivity,
2 minutes.
Yes. Coercivity is the ideal property that we would like for this problem. So what I did is restrict to, discretize the set of potentials. And our new functional is, we can prove that it's then coercive. And hence there is a maximizer, and we obtain a sequence of potentials such that some excited or ground state density have the target density. I don't present the numerical problem, which relies on a form, some degenerate Hellman-Feynman formula, which is this one. But I just wanted to say that it works, and that if we take into account those degeneracies, everything works. Sorry. And I will just conclude on what we learned from that is that there is no uniqueness, so no Hohenberg theorem for excited states. This comes from simulations. Then we obtain a way of constructive way of invert the map for mixed states at any precision for any k. And for the case of pure states, for d equal 1, we can prove that it's invertible, theoretically. For d equal 2, simulations show that it's invertible, but I don't know how to prove it theoretically. And for d equal 3, actually there is a counterexample by Lieb, and this also relies on the continuity of the Lévy-Lieb functional. But the answer is that there are densities which are not invertible for pure states. And finally, to finish, we also get an algorithm enabling to invert the map and to do what we want in any case. And that's it. Thank you for your attention.
Thank you very much. We have time for a quick question. Anybody in the audience, or maybe there's one online? No? So maybe just, I can ask a quick question. So in your first theorem, right, so you talked about weak, strong continuity, and then discontinuity of the inverse. Is that one follows from the other, or these are just independent statements? I'm not supposed to understand one from the other.
Sorry, what was the second one?
So the discontinuity, that's a separate statement. That did not follow from the continuity of the map. I mean, you had sort of the statement that the map was continuous, and you concluded, it seemed to me, that the inverse was discontinuous, but is that not logical?
Yes, it's from the weak strong continuity of the direct map, you can deduce the discontinuity of the inverse map.
Okay, maybe I don't see that immediately, but maybe is there a 30-second explanation to this fact?
So if you restrict to bounded domains, actually you prove that the map is compact. Weak strong continuity implies that the direct map is compact, and from the compactness, it's a topological argument that I don't remember, but you can. The image is small topologically, so you can say that there is no discontinuity.
Okay, thank you very much. So let's thank Louis again. So our next talk is online. That's Javier Buitrago Aza from Bogota. Javier, the floor is yours.
Thank you. Could you hear me?
Yes, we hear you well.
Okay, thank you. Okay, thank you for this opportunity. I'm Javier Buitrago Aza, and I would like to show you in this occasion this work that is entitled a C2 index for ground states of interacting Fermion systems. This work is in collaboration with Lucas Musnik and Andres Fernando Reyes Lega. So what is the main motivation of the work? So I would like to talk about what is the index I am referring in this talk. So basically, this index will refer to C2 index that will classify parity sectors in the set of quasi-free ground states for fermionic systems. This is in close relation with the parity of fermionic Fock ground states. And for other authors already used this index for understanding, for example, K-type chains with different boundary conditions, and also have some connection with non-commutative geometry, because it is possible to understanding this index by using orthogonal complex structures. So the people try to work with a split property in order to understand what happened with its connection with infinite chains. For example, Matsui that do that, and this also is in close relation with the parity of states proposed for Kita-F for understanding quantum wires. So here I will present a result that generalize in some sets the dimensional results in the sense that we can prove that for d-dimensional weak interacting fermion systems that index is stable. So basically, I will mention on some few things regarding the mathematical we use. Is considered self-dual Hilbert space that is only a Hilbert space that has some anti-unitary involution, and it is possible to define a self-dual CAR C-star algebra in such a way that we have a kind of CAR relations, and this B star only is defined by this B and my involution. So Araki showed that C-star algebra is isomorphic to the usual CAR C-star algebra that is generated by the annihilation and creation operators that are the usual operators when I study fermionic transport problems. So in this setting, I will consider a state that is only a normalized positive linear functional. And I will say that a state is a ground state. It satisfies this inequality, and for any in the domain of my generator associated to the dynamics of my system. So if I define a one particle Hamiltonian with a spectral gap, it is possible to describe the quasi-free ground states associated to that Hamiltonian by the following formula, where A plus is only the spectral projection associated to the positive part of the spectrum of my Hamiltonian. So note that it is possible to define a well-defined projection by this formula by using only a ground state, a quasi-free ground state. So it is possible to exploit some properties of my ground states in order to define projection like this. So the index I referred in this talk is the following. Consider well-defined projections, and the hierarchy index is this. So here, this wedge operator only refers to the intersection of the range of the projections, of the two projections. So basically, the index will distinguish if two representations associated to the positive Fock space associated to my projections are unitarily equivalent to the other Fock representation. So we can prove that if we consider a continuous family of one particle Hamiltonians with some gap are in the same phase of matter, so the index it will be 1 if I take any Hamiltonians in that family, and it will be -1 if I have other case. So what about the stability of the index? So I will consider a crystal lattice, CD, and I will consider the Hilbert space, this Hilbert space, L2. And it is possible to define a set of boxes, as is usual in the context, by the following. Here, L is any positive real number, and here I have a set of this PF CD refers to all the finite subset of my crystal lattice. So I can endow to the crystal lattice by a star algebra, but it's generated by the identity and some operators. Here AX will refer to some canonical orthonormal bases associated to my Hilbert space. So an interaction is defined as is usual. It's only element in the even part of my star algebra, and I will consider, for simplicity, a full interaction like a free part interaction plus interacting plus the interacting interactions. Sorry, and I can define in this talk and in general an interacting Hamiltonian like a free part Hamiltonian plus an interacting Hamiltonian, an interactive that has the interacting component of my fermions, of the fermions. So I take that H and I can consider some positive real number beta that is the inverse of the temperature in order to define the Gibbs Keynes states by the following. So here trace A refers to the threshold state associated to my star algebra. Okay, what about the main result? Take any finite range translation-invariant interaction for simplicity, and take beta going to infinite. So I will consider that the one particle Hamiltonian has some spectral gap, and I will say that the interaction is small enough. So first of all, it is possible to prove that the partition function associated to that Hamiltonian is uniformly analytic for some lambda in some open interval, where R, G, infinite will only will depend on the spectral gap, and it will depend. It will independent of the temperature and also of the size of the system. So I will choose some positive real number that depends only of my spectral gap, and it is possible to prove that there exists some lambda in that open interval in such a way that I can approximate in a suitable way the ground state associated to the interparticle system and approximate to the ground state associated to the free system. In this case, these two ground states will be translationally invariant. Okay, and as a corollary, we have the following stability of the system. Consider be a continuous family of one particle Hamiltonians in the same phase of matter. So for lambda is small enough, it is possible to prove this quantity. So one sketch of the proof is the following. So consider be a translation invariant interaction, and it is possible to analyze the minimizers associated to the energy free and linear functional that is defined by this, as is usual. Beta is some positive real number, and it is possible to prove the existence of the ground states because by using some techniques. In particular, for translational invariant states, this quantity exists, and that minimizer, it will be the ground state of my system.
2 minutes, please.
Okay, thank you. So it is possible to write the Keynes state as a very thin integral. Here, these variables, here, this omega will contain all the information associated to the one particle Hamiltonian, to the interacting Hamiltonian. This quantity refers to some covariance, and in particular, that covariance have charge bounds associated to the determinant and the Pfaffian. And it is possible to prove that for gaped Hamiltonians, that summability in the two-point correlation function associated to that covariance is finite. So by using some interacting kernel associated to my interaction, I can prove that by using Bridges kinetic expansion that this quantity for beta going to infinite is uniform volume, have uniform volume analyticity properties for lambda around 0. So the stability of the index follows from for know that it is possible to connect any two Hamiltonians in the same phase of matter, and knowing that for weak interaction the gap doesn't close, and it is possible to connect any ground states, the interacting ground state and the free ground states by some automorphisms. So symbolically, I will denote by this. And also, it is important to know that it is possible to define the index in terms of quasi-free ground states in such a way that it is possible to use the main theorem I presented to you because it is possible to show that the ground state associated to the interacting Hamiltonian is close enough to the free Hamiltonian in such a way that by using some arguments, the index it will be stable. Okay, some perspective of the question. So understanding other fermionic transport interacting fermion systems, and probably this result will have some contribution in the relation between K-theory and interacting fermion systems. This is in our work. This work is in progress, and also it's interesting to know if we can put in, symmetries for my Hamiltonians, and knowing other more general index. So what happened, for example, for other indexes in the free fermion case, if it have some relation with the index I present in this presentation. Okay, thank you.
Thank you very much. We still have a minute for a quick question, either from the audience or online. Yes, there's one. Please go ahead.
Hi, could you please comment on the topology in which you measure the closeness of the two ground states, the free one and the interacting one?
The topology, sorry, could you repeat, please?
So you say that this omega of the h lambda and omega of h without lambda are close. Could you comment in which sense they are close?
They are close in the sense that I can approximate for any, for any epsilon and maintaining the spectral gap open, it is possible always to approximate. In that sense, I am saying that are close. Always I can show some epsilon in such a way that I will find some interaction or some lambda that will control, I don't know, the distance between the two states.
Okay, thank you very much. So let's thank Javier again.
Thank you.
And we will move to the on-site system again. Our next speaker is Marius Lemm. The slides are up, very good. So he will speak about finite-size criteria for spectral gaps and random translation-invariant Hamiltonians. Please, Marius.
Okay. So first of all, thanks to the organizers for the kind invitation to speak here. Hi to you all. Thanks for sticking around. I think this is halftime, so you can all relax and stretch.
You have to talk closer to the microphone, I think.
Oh, sorry. Aha, thanks. I know how much you heard, but okay, I'll just start with the talk. Finite size criteria for spectral gaps and random translation-invariant Hamiltonians. I want to jump in by recalling a little bit of the background for quantum spin systems and the spectral gap and why we care. Then I want to survey some results and focus on one of them. So on a high level, what's a quantum spin system? I think the main feature that distinguishes it from other many-body systems is that particles are fixed to a lattice and interactions are bounded and local, typically. Okay? So there's a caricature here on the slide, right? So there's some 4x4 grid, and the particles are really fixed. There's no kinetic energy. I'm going to be working on finite systems. So the Hamiltonian is really just a big Hermitian matrix, and we're interested in its low energy spectral properties. So in particular, the ground states and the lowest excited states and the spectral gap between them. And in the end, to have a meaningful question, we want to take system size to infinity. So let me recall, this is familiar to many of you, the basic mathematical setup for a quantum spin system. For simplicity, I'm going to focus on nearest neighbor and translation-invariant interactions. So the Hilbert space, the state space of the system, is given as follows. Let me fix a finite graph lambda. And then at every vertex in the graph, I put a spin described by CD. Hilbert space, also called a QDIT in quantum information theory. And then the total Hilbert space is given as usual, just by taking the tensor product over all the sites. So this is, notice that this is exponentially large in the physical system size. And then for simplicity, I'm going to focus on nearest neighbor translation-invariant interactions. That means I just have to pick once how a pair of spins that are neighbors interact. And this is encoded in this matrix little h for sort of local little Hamiltonian. And this acts on the space of two spins. The space of two spins is CD tensor CD. So it's a d squared by d squared Hermitian matrix. And then I embed it into the operators on the big Hilbert space in the usual way. Let me see if the pointer works. Yeah, kind of. By tensoring with the identity. So hij is an operator that acts as h on I and j nearest neighbors and acts as the identity everywhere else. That's now an operator on the big Hilbert space. And then I take a Hamiltonian that's just the sum of all those local interactions. Okay, so this is quite a general quantum spin system subject to these restrictions, nearest neighbor and translation invariant. Okay, these are the kind of big Hermitian matrices I alluded to that I want to study down there. So what is the spectral gap of these? Well, I can order the spectrum. Let me define the eigenvalues with degeneracy. So E0 is strictly less than E1, but I allow for E0 to be degenerate. And then the spectral gap is just the difference between the two lowest eigenvalues. Of course, there are lots of gaps in the spectrum, but the lowest spectral gap is what's most relevant for low energy physics, and this is a condensed matter physics system. So we're interested in the bottom of the spectrum. Then there's a basic dichotomy. Now you have this positive number, the gap, at every fixed system size. And now imagine you take the thermodynamic limit. You have some sequence of graphs, say boxes in ZD, and you take the side length to infinity, then you have a sequence of positive numbers, gamma, lambda, L. And the question is, does the sequence go to 0 or does it stay away from 0? That's a basic sort of box in which you can put any Hamiltonian family in this, defined this way. You can put either in the gap box when the gap stays open, or you can put in the gapless box where the gap closes. And we're especially interested in the gap case, so when the gap stays bounded from below. And the reason for this is ultimately that we're interested in ground states, because we're not just interested in the number of the gap, but we're interested in describing physics. Ground states are complicated objects, but the existence of a gap gives you strong qualitative information on the ground states. And these are summarized here at the bottom. I don't want to go through all these in detail due to time constraints, but let me just say very quickly, if you're a ground state and you have a gap above you, we know that you belong to a very particular corner of the Hilbert space of states that have controlled complexity. And this is manifests in different ways. From a statistical mechanics perspective, the exponential decay of correlations is perhaps most natural. From a quantum information theory perspective, it's probably the area law for the entanglement entropy. And as you all heard during Yoshiko Ogata's talk, and we're reminded of, quantum phases are defined by connecting ground states of gapped Hamiltonians through paths. So the fact that a gap stays open is intimately related to the classification of quantum phases. So a different way to put this, if a deformation of the Hamiltonian preserves the gap, it preserves the phase. And then the gaps are also perturbatively stable, which is a related condition. Okay. So if I've convinced you that the gap is an interesting quantity to look at, it's probably unsurprising that it's difficult to prove that the gap stays open, because there's no free lunch. To highlight this, there's a famous conjecture by Duncan Haldane from '83 that the antiferromagnetic spin 1 chain, any integer spin chain, is gapped. That's a one-dimensional spin chain, and it's arguably the simplest antiferromagnet. It's isotropic, but we cannot prove this is gapped. Okay? It's still open. So reasonably, we want to add a helpful assumption to study, to get somewhere, and it turns out the correct assumption is frustration freeness. What's frustration freeness? Well, for normalization purposes, let me just say that the local interaction is a positive semi-definite matrix. All its eigenvalues are positive, so the Hamiltonian then has spectrum on the positive real axis. And then the real assumption is in the box. The real assumption is that the ground state energy of the Hamiltonian is 0. In other words, there's a state that is in the kernel of all the little h's. Okay? From the perspective of constraint satisfaction problem, that means none of the local constraints frustrate the other ones, hence the name. This is extremely useful for studying the spectral gap. Why? Well, essentially, if the ground state is perfect everywhere, then you know what excitations are. You just have to add local excitation energies. There can't be any cancellation of local excitation energies. And this is crucial for having finite-size criteria, which is going to be on the next slide, the method that I want to talk about for proving spectral gaps. Okay. Oh, I can't go forward anymore. Uh-oh. Oh, no, uh-oh. There's just the lag. Okay. Very good. So on this slide, I just want to present the first historical finite-size criterion, which I think is very instructive. So let me take two 1D chains. HL is an open chain of L spins in a row, and HLPER is just where I turn it into a ring by adding the interaction between the last and first spin. And then I have a gamma L, the gap of the open system, and gamma LPER, the gap of the periodic system. And the following theorem was proved by Knabe in '88, inspired by the famous AKLT paper. And so Knabe assumes, first of all, frustration-free, but we're going to have to assume this. And for simplicity, that the interactions are projections. That's not a big restriction. And then the bound that Knabe proves relates the gap of the system at different boundary conditions and different system sizes. There's a little L and a big L. Think of little L as 3, 4, 5, or 6, and think of big L as infinity. Okay? The point about this is that it gives a lower bound on the gap of the big system with periodic boundary conditions by the gap of the small system minus the threshold. So how do you use this in an application? Suppose, this is summarized in this corollary, suppose for some little L, say little L equal to 7, you can prove that gamma 7, by hook or by crook, is bigger than 1/6. Then you win, then you apply this theorem, and then you get a lower bound for large enough capital L's. Okay? This is how you use this finite-size criterion. The main point is that there's no big L appearing on the right side. Okay, and then this method has been improved in the last couple of years by various people that are summarized at the bottom here, but I don't want to sort of go into the details of that. Rather, talk about, first of all, this is a kind of a summary slide. How can one apply this? So the basic message of this is that you can use these finite size criteria in some concrete models to derive gaps, okay? And at the top is sort of just a kind of high-level summary how one could implement this. If you're trying to prove some inequality like gamma little L is bigger than 1 over little L minus 1. There's basically two ways to do this in practice. One is that you actually have a family of models that depend on a parameter that positively affects the local gap, the finite size gap, and then you prove analytical estimates that show you that if the parameter is big enough, then you can verify the finite size criteria, and then you get an analytical proof of an infinite volume gap. The point of the finite size criterion, it gives you a rigorous way to extrapolate to infinity once the finite size information is good enough. The other possibility is that you're just looking at a fixed model which just has some finite size gaps and you just have to compute them. And typically this can only be done numerically and then typically also only non-rigorously. And so there's some examples at the bottom of the slide where this was implemented in recent years with various co-authors. Many of them are here. But I want to instead, given the time constraints, focus on a slightly different perspective on the issue. What's another way to get some wiggle room in a Hamiltonian, right? Wiggle room helps you a lot. That was this model parameter idea up here. And the other way to get some wiggle room is, of course, to take a probabilistic perspective.
2 minutes.
2 minutes, thanks. That's good. So this was motivated by a paper by Rami Smovasag, who proved that if I take the local interactions, all independent GUEs, all independent GUEs, then the probability of having a gap is 0 in any dimension. The question arose, what happens for translationally invariant Hamiltonians? And the question is then, what's a random translation invariant Hamiltonian? So here's a proposal for that. So I take an interaction H that's a random projection of fixed rank. How do I get a random projection of fixed rank? For example, I can take a Haar random unitary and take its first R columns. I'll look at the projection onto that space. Okay, this is a random projection of fixed rank. And then this samples my local interaction. Now I put that random local interaction everywhere. Put the same one everywhere. This gives me a translation invariant Hamiltonian defined like in the bottom here. And let me just go on a ring again for simplicity. Okay, so I've randomly sampled once, random projection, now I put it everywhere. And the theorem one can prove is that if the local rank is small enough, that's important for reasons I'll explain on the next slide, then there's a positive probability that these are gapped. Okay, that's the result. So this, I want to point out, right, this says the translation invariant case is completely different from the spatially disordered case. Gaps are much more common in this sense. There's a previous result by Bravi and Gosset, who proved that for d equal to 2, which means rank 1, the gap is positive almost surely, actually, so the probability is 1. The proof I found just gives a very bad, explicit but very bad bound on p epsilon. The proof idea, unsurprisingly given the talk so far, is that you want to show that a finite size criterion is verified with positive probability. Well, why the small rank assumption? Where does that come from? Well, small rank ensures that you're frustration-free deterministically. This is absolutely crucial, and I have no idea how to do it for huge ranks. So small rank is sufficient, but not necessary for frustration-freeness. There's various extensions of the result to trees. That was done in the original paper. More interesting is an extension to higher dimensions, and this connects to a recent breakthrough of proof of the area law for ground states of two-dimensional frustration-free models. And I think this would have applications there, but I don't have really time to get into that. So let me just say, the main message I want to convey today, finite size criteria are very rough. You're asking a lot. You're asking for the system to be really good locally. Very rough method, but effective method for some models if you have a parameter to play with for proving spectral gaps in quantum spin systems. There's a list of open problems and future directions, but I don't think there'll be time to go through that. So thanks very much for your attention.
Thanks, Marius. Any quick question or comment? Yes, Wojciech.
I don't know what it works.
Well, now it stopped working.
Yes. So you mentioned that there is a proof that the gap is open almost surely in 2D, whereas the theorem that you stated in 1D seemed to be weaker. So is there a problem?
There's two Ds. Yeah, this is confusing. The little d is the local Hilbert space dimension. The big D is the global dimension. So my result and their result works on chains, right? Which are big D equal 1. The little d means spin 1/2. That's another way to say that.
Oh, okay.
Yeah, thanks for the question.
So let's thank Marius again for the nice talk. So we continue with another online talk by Simone Rademacher. I see Simone, just waiting for the slides. Very good. Okay, so the next talk is by Simone Rademacher, the dynamics of the strongly coupled polaron.
Yeah, so first of all, thanks to the organizers for giving me the opportunity to present some results that I obtained in collaboration with Dario Felice-Langeli, David Mutruskas, Nikolai Leopold, Benjamin Schlein, and Robert Seiringer about the dynamics of the strongly coupled polaron. So the polaron is a model for an electron that we consider in an ionic lattice. So these blue dots here are the lattice ions, and they are positively and negatively charged and have a fixed position in the lattice. So what happens now is that the electron, it attracts the positively charged lattice ions while it repels the negatively charged ones. So effectively, it will be surrounded by a self-induced polarization field that in physics one often describes through quantized phonons. And as my title suggested, I will consider the dynamics of the polaron. So the polaron is the entity of the electron with the self-induced polarization field. And what happens is that the electron moves together with these cloud of phonons through the crystal, and effectively these interaction with the self-induced polarization field will slow down the electron. And since in physics one can always relate a decrease of velocity with an increase of the mass, effectively the electron has a larger mass than moving through these crystal. So to come to the mathematics behind, on a quantum mechanical level, the polaron is described in the Hilbert space that is the product of the Hilbert space for the electron, that is L2 of R3, and the one for the phonons, that is simply the bosonic Fock space. And the bosonic Fock space is equipped with the standard creation annihilation operators. We already saw a couple of times. They satisfy here the standard commutation relations. And with these notations, we can now write down the Fröhlich Hamiltonian that is known to describe the polaron, and that is the sum of three terms. So first of all, we have the kinetic energy of the electron, so it's simply the Laplace operator acting on the electron only. Then we have here the one of the phonons, so that's simply the number of particle operators acting on the phonons only. And then we have the very important interaction term. So it's acting on both. It's acting on the phonons through the creation annihilation operators, and through these x variable here indicated here, it's acting on the electron as well. So the potential it's acting on the electron with is written down here. It's simply a dipole potential. And it's also important to notice that the interaction term comes with a square root of alpha in front. And so alpha is bigger than 0 and simply denotes the coupling constant. And as the title suggests, we're interested in the strong coupling regime. So alpha, you can always consider alpha tending to infinity. And in this particular regime, it turns out to be useful to rewrite the Hamiltonian in so-called strong coupling units, which means that we consider rescaled creation annihilation operators that I will name B in the following. And they are rescaled because their commutator here comes with an alpha to the -2 in front, while here the commutator of the rescaled creation annihilation operators among each other, they're still vanished, they are still the same. And then we can rewrite the Hamiltonian in terms of the B's, and the coupling constant here in front drops out. And the dependence now on the rescaled Fröhlich Hamiltonian on the coupling constant alpha is now completely hidden in the creation, in the modified creation and annihilation operators. So these strong coupling units, they are not only very convenient for computational reasons, but also to already get a bit the idea behind the strong coupling regime, namely since we consider alpha tending to infinity, this means that in this limit, the commutator of the B's vanish. And so we can somehow expect that the phonons behave classically in the strong coupling regime. Right, so we are interested again in the dynamics of the system. So what we consider in the following is the solution psi t of the Schrödinger equation generated through these rescaled Hamiltonian H alpha. And we will consider very particular initial data, namely data of pK product form, as they are called. So which means we have a product state in the sense that here we have an electron and function, and then we have the phonon field, and they are not coupled. And in particular, so W denotes the Weil operator. We can see here that we consider the phonon field to be initially a coherent state, which also coincides with this picture of having a classical field. This state is called pK product state because pK used it or introduced these particular states to derive the first order of the ground state energy of the polaron. So the question will be how good in the classical, in the strong coupling regime, the classical approximation of the polaron will be. And so we first need to define what is the classical polaron I'm speaking about. And this basically comes from the picture and replacing these creation annihilation operators B simply by an L2 function phi. So the classical polaron is a couple psi and phi, which is an H1 function, so that's the electron, and phi, the phonon field, is an L2 function. And then the classical polaron is described through the pK functional that is given as the following energy functional. So it's the expectation value of the electron wave function in with respect to the Hamiltonian H phi. H phi is simply the sum of the Laplacian and the potential generated through the phonons, and the L2 norm of the phonon function. And then Lieb showed that there exists a pair of minimizers, the so-called pK minimizers, so psi p and phi p. And so psi p is simply the ground state of the Hamiltonian H phi p, while phi p is explicitly given in terms of psi p as well, where the function sigma I wrote down here. And then in the following, I will always call the ground state of these pK functional as EP. So these energy functional gives also rise to an dynamical equations, namely the so-called Landau pK equations. So that's a system of a coupled these are two coupled differential equations, and so one for the electron that you can see here, and actually the electron satisfies an Schrödinger equation with respect to this Hamiltonian H phi t, depending on the phonon function, while the phonons satisfy a classical field equation. So this is again the picture that in the strong coupling regime we have this classical behavior of the phonons. And what is also important to notice is that the time evolution of the phonons comes with an alpha square in front, which means, again, in the strong coupling regime that we have a separation of timescales. So the phonons vary on much larger timescales than the electron does, which was very important for our calculations. Right. So to come back to our problem, so we raised the question, so if you start initially with these pK product state and consider its time evolution with respect to the Fröhlich Hamiltonian, can we expect that after some time t we can still approximate it with a product state where psi t and phi t are somehow given through the Landau pK equations? So this was the question we were interested in. And we answered this question by the following statement, namely, we compared exactly this time evolution of the pK product state, and then we showed that you can approximate it by a product state, in the sense that here you have, again, the product of the electron wave function, and here you have the state of the phonons. And then the difference of these two states are bounded by constant times alpha to the -1. Times an exponential, and this exponential is small whenever t is on timescales order alpha square, which means this is a good bound for all times order alpha square. But it's important to notice that the state we are approximating our time evolution width is not a pK product state. It's a product state, but omega t, you can see here, is depending on the time. And in fact, it's the solution of this equation here. So it's the solution of the Bogoliubov dynamics. And this was somehow the crucial step on these timescales, that in order to get a normal approximation, you can still approximate the dynamics of a pK product state by, again, a product state, but you have to adjust a bit the phonon state, in the sense that you have to introduce some quantum fluctuations that this Bogoliubov dynamics is taking care of. And actually, another thing that is important to notice is that we consider here a very particular class of initial data, namely, we consider here the initial electron to be the ground state with so for a fixed phonon field phi 0, we consider the electron to be in its ground state initially. And additionally, we also want that the energy of psi phi 0 and phi 0 is sufficiently close to the ground state, so sufficiently small. And this particular states we have to consider, because we have to ensure somehow that we have a uniform spectral gap, uniform in sine and alpha, for all times that we consider. And this we can only prove.
Simone, just 2 more minutes.
Okay, thanks. This we can only prove for these particular states. Another nice thing that comes out from our theorem is that you can, we also get a result on the level of reduced densities, namely you can approximate the reduced density of the reduced density of the electron by the projection onto the Landau projection onto the solution of the Landau pK equations, and the same holds true for the reduced densities of the phonons. And here you don't see the Bogoliubov dynamics at all. Right, another result I quickly wanted to mention is about the mass that I mentioned at the very beginning, and that is somehow also very closely related to the dynamics, that because we saw now that the Landau pK equations give somehow a good approximation for the dynamics of the system. And Landau and pK formulated this very famous prediction about the effective mass of the polaron, namely that it diverges in the strong coupling regime as alpha to the 4, and they even predicted the constant that it is diverging with. And so far, there's very little known about these effective mass. Actually, there's one result about the full quantum model of the polaron, so governed by the Fröhlich Hamiltonian, by Lieb and Seiringer, who showed that based on an energy momentum expansion, the effective mass of the polaron diverges. And what we did now is to consider the classical polaron. So it's really only that is defined on the Landau through the Landau pK equations. So it's really only on this level only. And then we defined the mass through an energy velocity expansion, namely in the following sense, that we considered initial data with fixed velocity v, and we considered the velocity to be sufficiently small. And then we can show that taking the infimum over all these initial states with velocity v, one gets the following expansion of the energy here, and then you can define the mass as the coefficient in front of the quadratic term of the energy expansion. And if you do this, then we get, as a result for the effective mass, the one here, which if you compare with the prediction of Landau pK, exactly coincides in leading order with what they claim. Right, so this was just a very quick outlook about that.
Thanks, Simone. Are there any questions, comments? Either online or on site? Yeah, Niels, go ahead.
Yeah, can you say anything about systems of more than one polaron by your methods?
You mean for the effective dynamics? I mean, I haven't thought of yet. I don't know. I would need to think about it. I think I would hope so, but I'm not sure.
Any other questions? If that's not the case, then let's thank Simone again for a nice and very well-timed talk. So we actually have 1 minute to switch to the Next speaker on site again. Very well, so I believe we start on the second with the next talk by Arnaud Triay on the dynamics of the Bose gas with three-body interactions in the Gross-Pitaevskii regime.
So I would like to start by thanking the organizers for this nice event and also for the opportunity to talk here. So I'm going to talk about the dynamics of the Bose gas with three-body interactions, in the Gross-Pitaevskii regime. And this is a joint work with Phantom Nam and Julien Rico from LMU. So we consider n bosons in R3 that interact through a three-body interaction potentials. That means that they only see each other if there are at least three in the same neighborhood. The energy is described by the following Hamiltonians. So we have a kinetic term, the usual one, and then this three-body interaction potential. It is scaled in the Gross-Pitaevskii scaling. We consider the n-body dynamics given by the Schrödinger equation. And we want to show that if we start close to a condensate, then this propagates through time. That after the n-body dynamics, we are still close to a condensate. And we want to show that the wave function of the condensate satisfies the quintic Gross-Pitaevskii equation, which is written here. I don't know if this works. Okay, and in this quintic Gross-Pitaevskii equation, there is a parameter B that is the three-body scattering energy. And in this regime, it is different from the mean field intensity, that is the integral of V. Okay, so a word about previous works. So previous works considered intermediate regimes that interpolate between the mean field regime and the Gross-Pitaevskii regime. So namely, they considered the following Hamiltonian, where there is this scale potential with a 1/n squared that plays the role of a mean field parameter, and this n to the 6 beta V of n beta scaling, where beta is between 0 and 1/2. So 0 is the mean field regime and 1/2 the Gross-Pitaevskii. And when beta is strictly smaller than 1/2, then one expects that correlations do not play a role at leading order. And in this case, the effective equation is given again by the quintic Gross-Pitaevskii equation, but the parameter is no longer this parameter that I denoted by B, that is the three-body scattering energy, but it's only the mean field intensity integral of V. So quickly, the result that is not yet on the archive, but I hope soon. So the first three lines are assumptions on the initial state. So we assume quite strong assumptions. So namely, the first one is a full condensation at time t equals 0. And then the second one is that the energy of the system is given at leading order by the Gross-Pitaevskii energy of the condensate, of the one-body wave function, and at second order by a correction term of order square root n that appears naturally in the analysis, and this up to error big O of 1. And we assume the same thing for the variance of the energy. What we can show is that for some epsilon positive, then we have Bose-Einstein condensation with this, with this rate here. So this is a cautious statement. I think we can take epsilon at least of order 1/2. Okay. So I will say a few words about this three-body scattering energy, and so what it is and how it is different from the two-body case. So because Hn has to leave invariant the n-body, the bosonic space, we need to assume some extra assumption on the potential V, namely that in the expression here, it should remain invariant if we exchange x, y, and z. Right, so I call this assumption delta. And in the analysis, it appears that the relevant quantity is in fact the quantity in the box, right? So it looks like the two-body scattering energy, but except that there is a matrix M in the kinetic term that accounts for the relative coordinates that you chose in the potential V. Okay, and M is the square of M is given by the expression below. And you see that this quantity is relevant. I mean, because if you minimize it, well, there's a unique minimizer that is called the scattering function, and the scattering function inherits the symmetry of V, the assumptions delta. Okay, and it actually makes a lot of sense because you would like to think of the many-body wave function as the expression below, that is a pure condensate dressed with a correlation factor that encodes the correlation among particles and where this F is involved. And you see that for this expression to be symmetric, then you need F to satisfy the symmetry delta. Okay, so now I apologize. I will go a bit into the detail of the proof. It was hard to say something interesting without doing so. So I will first recall the setting, the framework, and then give some key elements in the strategy of the proof. So we work in excitation space. That is, we consider the solution of the Gross-Pitaevskii equation, phi, it's a one-body wave function, and we describe psi n, the many-body wave function, in terms of its and the excitations with respect to this one-body wave function. Right. We call this excitation vector phi, and this way of describing the system was formalized in this paper of Levin, Nam, Sarfati, Solovay. So now this transformation is unitary, and you can also transform the Hamiltonian. You obtain a Hamiltonian on the Fock space. And this excitation vector phi has a dynamics generated by G, which is denoted here. So it's composed of two terms. So the right term is just the new Hamiltonian under the unitary transform. And the first term is just a drift due to the fact that you're describing excitations with respect to a moving frame. So in this formalism, what we want to prove, I remind you, is that the left-hand side here, I don't know if this works again, is a little o of n. And it turns out that you can rewrite it in the Fock space as the average of excitations of this excitation vector phi. Okay. So in the mean-field regime, what you do is that you apply, one proof is to just apply the Grunwald lemma to this quantity. You see when you differentiate it, it becomes the expectation of the commutator of G and N. And for the proof to work, well, you hope that in G, there are only terms that either commute with N or that are small. And if you look at what G is, so it's just the transform Hamiltonian, and then there is a drift term. And the only term in the transform Hamiltonian that does not satisfy the two previous conditions is L1. And this L1, in the midfield regime, is just killed by the drift term. Of course, this strategy is not possible in the Gross-Pitaevskii regime, so we need to focus on a bigger quantity, a bigger conserved quantity, on which we want to apply the Grunwald lemma. And this quantity is the generator of a renormalized dynamics that I will explain, I will give later. And this generator of this renormalized dynamics, you can show that it is approximately conserved by the dynamics, and that it controls the kinetic and the L6 part of the Hamiltonian, up to some order n to the delta, that is the precision of your approximation. Well, it turns out that because of some other terms, namely the L4 and the L5, you will see them later, we need to localize in a sector of particles of at most square root n particles, in a way that was introduced by Nam and Napierkowski. But because we need to localize on this sector of particles of at most square root n excitations, we also need to refine the analysis and to have a precision that is little o of square root n. Okay. And for this, we also need to do implement a second renormalization to kill the L2 terms. Okay, and we combine methods that were known already in the two-body case that were studied extensively and by all those people that I don't have time to cite properly. Okay. So this is the renormalized dynamics. Okay, so we work on, so it lives on the sector of at most m particles, where m is much smaller than square root n. And it's driven by this generator GRN, and it's essentially equal to the drift from the beginning, plus this transformed Hamiltonian, and where T and S are unitaries, which are given below. And it works, so T is sort of the generalization, the natural generalization of the two-body case. So you see F is just a scattering function, and then you just put three creation operator to kill the L3 term, which is of order n. And then because of what I tell you before, that is we need to kill the L2 term to go to a precision of order little o of square root n. We also need to renormalize a second time with a quadratic transform, which is in green, I think. Okay, and we worked only on phi m, and we show that this generator is approximately conserved. And by this, I mean, this allows us to show that actually phi m is a good approximation in norm of the real dynamics psi n of t. Okay, and this, of course, implies Bose-Einstein condensation. So now, let me show you a bit how the renormalization works. So don't be afraid, there are many terms. So this is what you get when you look at the Hamiltonian in excitation space. So the first term is just, L naught is just the mean field energy of the system. It's of order n, which is quite big, but it's fine because it's a constant, so it commutes with everything. If you want to, if you want to reproduce the proof of the mean field case, then the first thing you want to kill is the L1 term. Of course, here, the L1 term has a mean field form, and it doesn't exactly cancel with the drift. And the reason why is that there are hidden contributions due to the correlations that you need to extract from the L4 terms. You see the L4 terms, it has these three A daggers. And by using the T transform, the cubic transform, you just replace those three A daggers by a scalar function that appropriately renormalize L1 for it to be killed entirely by the drift u dot star un. Of course, this transform acts on all the terms, and it also kills the L3 term, which is of order n, which is nice, and renormalize the L naught term to give the Gross-Pitaevskii energy and not the Milfin one. It also renormalizes the L2 terms with contributions hidden from the L5 terms, because you see in the L5 terms you also have those three A daggers. Okay. Now that you've done this, you're very happy at first, because well, the L naught term commutes with everyone. The L1 term is gone. The L2 term, you can show that it's of order square root n. So this is fine because you want precision up to little o of n for the moment. And the L3 term is gone. Unfortunately, there are the terms in L4 in the brackets that we don't know how to bound them except by the quantity on the right. That is the kinetic term times the number of excitations divided by square root n. And this suggests that we need to go to a sector of particles of at most square root n particles. Okay. And this, for a reason that I don't have time to explain, requires to have a precision of order little o of square root n, and square root n is exactly the order of L2. So we also need to kill L2 by a second transform, which is the transform S presented before, which we do, and it allows us to close the argument. And I thank you for your attention.
Thank you very much. Questions or comments? Yeah, please go ahead.
Thank you for your talk. I was actually just wondering, these three body interactions, do you know to which degree they are experimentally realizable?
Sure. So that's the next slide. No. So two-body forces, they are already two-body potentials are already efficient, right? So if you have a compactly supported non-negative potential, well, it's probably not fundamental. And so the three-body potentials, you can see them as corrections to two-body ones. But so if you have a system of particles, well, for computing their effective two-body potential, you just take two of them, and then you integrate the internal degrees of freedom. But then if a third one shows up, then maybe the internal degrees of freedom change, and then the effective two-body potential is not valid anymore. You need a correction. I hope this answers your question.
Any other questions? Yeah, Marcin?
So if you add also two-body interactions, would you derive a cubic quintic NLS?
Well, I guess so. At least for the ground state energy, I think this is easily feasible. And this is what Nam will talk about tomorrow, I think.
Can you maybe just say a word about this E2, right? In your assumption, you had sort of a second order energy assumption. You said it was something natural.
Yes, so it actually comes from the second renormalization, right? So it's, as I said, the L2 term is of order square root n. right? And then it contributes to this E2 term, right? And there are also some other terms coming from the L4, right?
Stefan.
Just a short follow-up. Is it known in this case that the ground state, if you put a confining potential, will satisfy your energy assumption?
So here there is no external potential, and we provide also initial data that satisfy those assumptions. In the ground state, I mean, Nam will talk about it. We know up to little o of n, but we don't know anything about the variance and so on. I mean, of course, the variance is okay, but.
Okay, thanks again.
Thank you.
So we continue right away as soon as the slides are up. The next talk is by Marcel Schaub. I'll read the title in the meantime. It's the BCS Functional in a Weak Homogeneous Magnetic Field, Critical Temperature Shift and Derivation of Ginzburg-Landau Theory. Please go ahead.
Thank you very much. It's a great pleasure and honor to speak at my first such large conference. So thanks for the time to report on these two results on the BCS functional of superconductivity. One of which is the critical temperature shift that it undergoes under the influence of a weak magnetic field, a constant magnetic field. And secondly, the Ginzburg-Landau theory that it displays in the weak magnetic field limit. So all I want to say is joint work with Andreas Deuchert and Christian Heinzel, my advisor, and you can find the article on the archive. Okay, so if it's loading, then I want to consider a sample of fermions that is living in a box, where the lattice ions are in red and the electrons are in green. And this sample is exposed to a constant magnetic field pointing in the E3 direction, okay? And it has strength B, which is a positive parameter. And I'm choosing the gauge here that I've written down there. And I'm thinking of this sample of being periodically extended to all of R3, such that I have a unit cell of my lattice of periodicity, which is spanned by these three basis vectors, B1 through B3, which are just stretched standard basis vectors by this factor of square root 2 pi B inverse, okay? And in this way, I model a system which has a constant non-zero magnetic flux through the unit cell, which is the new part in this enterprise of the BCS functional. So BCS theory amounts to having an attractive interaction potential, which you can think of as minus a positive function V between the particles, which causes the particles to undergo a Cooper pairing mechanism, which I depicted by these colored clouds here. Okay, this pairing mechanism takes place below a certain critical temperature, which I'm going to explain to you in a minute. And I'm interested in the weak magnetic field regime, which means that I'm taking B sufficiently small. This causes the box to be macroscopically large as opposed to the microscopic interaction between the particles. Okay, so I have a two-scale nature of the problem, and the square root of B plays the role of a semi-classical parameter. Now, mathematically speaking, BCS theory is an effective two-particle theory where the states are described by a one-particle density matrix, capital gamma, with two components. It is a self-adjoint operator, trace class between 0 and 1, and as we know, the first entry in this way is also self-adjoint between 0 and 1. Its trace per unit volume models the density of the system, and the kernel of alpha is the Cooper pair wave function, which is symmetric with respect to exchange of the coordinates because I'm neglecting spin in my system. And then I have this relation between the two, which comes from second quantization. So the BCS free energy functional then is defined with three terms: kinetic, entropic, and interaction term. And the kinetic term is the trace per unit volume of the magnetic Laplacian acting on gamma. I have the usual entropy term, which is given by the trace of gamma log gamma, and then I have this attractive interaction part, which is just the Hilbert-Schmidt scalar product per unit volume of alpha times alpha. So if I, for the moment, neglect the interaction, then I find that this energy functional is minimized by a state which is diagonal, meaning that alpha is equal to 0, and the gamma is the usual Fermi-Dirac distribution of the magnetic Laplacian, which I would then call the normal state. And if the interaction is turned on, then the state may be unstable for certain temperatures, which I would then call a superconducting state. Which brings me to the definition of the critical temperature, and this is defined in terms of the translation-invariant functional at B equals 0. And as an old result by now from 2008, it is remarkable that I can find such critical points of the functional by just looking at minimal perturbations in direction alpha of the normal state. So I'm concerned with considering the Hessian matrix of the functional, which is given by this linear operator kt minus v, where kt displays the kinetic and entropic part of the functional, and it has this peculiar dispersion relation p squared minus mu over the tanh. So if I now want to look for positive definiteness of this Hessian matrix, I need to identify temperature regimes in which this kt minus v operator is entirely positive, meaning that it has entirely positive spectrum, or not. So since this operator kt is monotone in T, I indeed have a unique critical temperature such that this temperature Tc separates these two temperature regimes. So this I displayed in orange here, and this is my critical temperature. So from now on, I will assume that the critical temperature is indeed positive and that the corresponding lowest eigenvalue is simple. And I will call the ground state eigenfunction by alpha star. And now I have to introduce to you my limiting theory, which is Ginzburg-Landau. So this is given in terms of a single order parameter psi. It consists of three terms: a kinetic term, a quadratic term, and a quartic term. And from the perspective of BCS theory, the psi squared models the density of Cooper pairs. So this is also the reason why there is twice the original magnetic potential appearing in the kinetic term, because a Cooper pair carries twice the charge of a single particle. And then you can consider the ground state energy of that model, and you see that it has a phase transition at a certain critical parameter dc, where this d appears in the quadratic term. And this is given by a linearized Ginzburg-Landau theory, which in my case is very concretely given by just the Landau Hamiltonian, whose ground state energy is 2. Okay? So the Ginzburg-Landau model is minimized non-trivially if d is larger than this critical parameter, and otherwise it's just minimized by 0. So this brings me to my main result, or the first one. Namely, if I consider the BCS energy, which is the infimum over all states gamma, compared to the energy of the normal state, then if I'm within a linear regime here from the critical temperature, then I see that to leading order, the BCS energy is given by Ginzburg-Landau energy. And moreover, if I have a minimizer gamma, then this Cooper pair wave function undergoes a decomposition into a product to leading order of two things, namely, first of all, a center of mass part of the wave function, which is modeled by psi, and a relative part, which is modeled by the ground state wave function of this linear operator ktc minus v. So in other words, the alpha star part is the microscopic part of the theory, which takes place in the relative coordinate. And on the center of mass part, you have the Ginzburg-Landau minimizer, psi, which is macroscopically extended throughout the sample and lives on the order square root of B inverse. Okay, so on the one hand, you have the microscopic behavior displayed in the relative coordinate and the macroscopic behavior displayed in the center of mass. So this result was earlier obtained by Frank Heinzel, Zaringer, and Solovay in the context of bounded periodic magnetic potentials where the flux was zero. And here, the main difficulty is really to obtain this decomposition result when you have to have a priori estimates that all the way carry through the magnetic field, because you cannot remove it perturbatively as opposed to the bounded periodic case. Okay? Second result pertains to the critical temperature shift. And unfortunately, my model with the present B is not monotone anymore, so I have to have two critical temperatures, namely first the upper critical temperature, which is the lowest temperature, such that above it, the normal state is always stable, and I have the lower temperature, such that below it, the normal state is always unstable, okay? And if I have this, then I can say that the critical temperature of the model is confined, or these two temperatures are confined around a linear behavior whose slope is precisely given by the critical parameter of the Ginzburg-Landau model. Okay? So this was earlier obtained by Frank Heinzel and Langmann in the context of linearized BCS theory. So in that sense, our result justifies this linearization and shows that the result is true for the full nonlinear BCS functional. Thank you very much.
Oh.
That was it.
Perfect. Thank you very much. We certainly have time for questions. Are there any questions, comments? Yeah, back there.
Yeah, so your B field change here, the temperature you're working at, your result, is very close to the critical temperature, and there's this linear change in the B field. Do you expect to be able to change this to go further from the critical temperature, or is this sort of critical?
No, actually, I don't think so. Because this Ginzburg-Landau theory, so all estimates you do are around the BCS functional. So what you have at hand is you really can evolve around this little identity here, yeah. And I don't think you can go very much further the order dB here. No, I don't think so.
So we have an online question.
Okay.
The participant thanks you for the talk and asks, what is the definition of alpha?
So alpha...
And maybe he just added, and why is it a good object to model the density of Cooper pairs?
Okay. So... okay, so maybe this is a bit bad answer, but so first of all, the definition here is the upper right entry of the one particle density matrix. The reason why it's a good object to model Cooper pairs is because it's a two-particle object that comes from second quantization, modeling the long-range correlations between the fermion gas. Maybe that's the best answer I can give.
Thank you. Are there any other questions or comments? If that's not the case, then I suggest we thank Marcel once more. And we come to the final talk of the session. We'll just wait a second until the relevant slides are up. Very good. So last but not least, we have Nikolai Leopold, who will talk about mean field dynamics for particles in interaction with quantized radiation fields.
Hello, everybody. First, I would like to thank the organizers for the opportunity to give a talk here at this nice conference. I would like to present an overview of some results on which I worked or currently work with Marco Falconi, David Mitruskas, Søren Petrat, Peter Pickel, and Robert Zeiringer. And the outline of the talk is as follows. First, I would like to start with a small motivation. Then I will talk about many boson mean field limits and many fermion mean field limits. And if time permits, I want to conclude with some remarks. So let's start with the motivation. In many areas of physics, physical phenomena are described by quantum fields. A famous example, for example, is the quantized electromagnetic field. However, in certain situations, one can already predict or make good predictions by classical fields. So the question arises when it is possible to approximate quantum fields by classical field equations. And in the talk of Simone Rademacher, we have already seen that this is possible in the strong coupling limit of the polaron. And in this talk, I would like to motivate that this classical emergence also appears if one looks at many uncorrelated particles which weakly couple to quantum fields. And the general setting is the following. So we have a Hilbert space which models n particles, and a Fock space which describes the excitations of the quantum field. Then the dynamics of the system is given by Hamiltonian, which describes the free evolution of the particles, the free evolution of the field, and an interaction term where the particles couple to the quantum field. And then we would like to look at the large particle limit of the system and initial conditions such that the quantum field can be described initially approximately by a classical field with mode function alpha naught, and such that the particle state can be described by a function psi n naught, which still can be n-dependent. And what we then would like to show is that this approximation also holds at later times where psi n naught, alpha naught evolve according to a self-contained effective dynamics. And in this sense, we would like to say, that we can at all times approximate the quantum field by a classical field. And in order to make this a bit more precise, I want to jump to the first model, which is the Pauli fields Hamiltonian. In our case, it describes n bosons which interact with the quantized electromagnetic field in the Coulomb gauge. So we have a Coulomb direct interaction for which we just apply the normal mean field scaling, and then we have a direct interaction term to the quantized vector potential. And if we look at the quantized vector potential, we have the usual creation and annihilation operators, and then we have polarization vectors and an ultraviolet cutoff. And if we look at the Hamiltonian again, then we see that we have a factor of 1 over square root of n in front of the vector potential. And this is chosen in such a way that, so to say, all terms are of the same order of magnitude. And next, I would like to motivate in which situations one can expect classical behavior. And then important, so to say, important states with this regard are coherent states, which can be generated if one acts with the so-called while operators on the vacuum. And these states are so important because coherent states are eigenstates of the annihilation operator. And if we, so to say, act with scaled creation operators on a coherent state with high occupation number, then it's an approximate eigenstate of the creation operator. So if we again look at our quantized vector potential with this prefactor 1 over square root of n, and we let it act on the state psi and t, then one can replace the creation and annihilation operators by complex numbers. So if the system is in such a state, we would expect that we can replace the quantum field by a classical field. And if one looks at the state psi n again, then one sees that for the particles I've chosen a Bose-Einstein condensate. And I've done this because one expects that a Bose-Einstein condensate creates coherent radiation, because then the quantum flux can approximately be approximated by its by the mean flux, and this should then lead to a coherent state. So if we could show that the structure is preserved at all times during the time evolution, we would expect classical behavior. And if one just takes this for granted, then one can, for example, look at the Heisenberg equations, and then one sees that the condensate wave function and the classical field should satisfy the Maxwell-Schrödinger equations. And this is a nonlinear set of equations, and here we see that the condensate wave function satisfies a Schrödinger equation where we have a Hartree potential which comes from the mean field scaling of the Coulomb potential. And then we couple, so this function kappa is just the Fourier transform of the cutoff function in momentum space, then we couple to a classical vector potential which can be written with a mode function alpha t. And this mode function alpha t satisfies an equation where the first part is just a free evolution, and then we couple to the quantum flux of the condensate and the classical field. And it might look a bit familiar, so to say one can rewrite these equations formally in an equivalent form, and then one sees that so to say the field satisfies the electromagnetic field in the Coulomb gauge. So with Peter Pickler, I could derive the following result. So if one initially has a condensate of particles, a coherent state of radiations, and the fluctuations of the energy per particle are small, then this A n, B n, and C n tend to 0 if n goes to infinity. And then the right-hand side of these two inequalities is small, and what does the left-hand side say? The first inequality just says that the one particle reduced density matrix of the particles, so if we trace out all degrees except of one particle, converges to the projector onto the condensate wave function, which evolved according to the effective dynamics. And the second inequality says, so if we, so to say, destroy a coherent state with function square root of n alpha t, and we look at the field energy above this coherent state, then this is of lower order than order n. And for photons which don't have very small energies, one can then say, so to say, that they have a coherent structure, and just that you don't have to worry about this HF, one can extend this result a little bit and then replace, so to say, HF by the number operator, and this I'm writing down in a small note with Marco Falconi currently. So next, I would like to look at another model, namely together with David Mitruskas and Robert Seiringer, I could derive a similar result for the Fröhlich model, which was also introduced in the talk of Simone Rademacher. However, this time we are not looking at the strong coupling limit, we are looking at the weak coupling limit and many particles. And one could expect that one can model with this Hamiltonian Bose-Einstein condensates with certain interactions which can be approximated by a phonon field. And also in this case, one can then derive as effective equations the Landau-Pk equations. However, this time we don't have a separation of scale in the Landau-Pk equations because we have a different scaling. And in comparison to the previous result, so we only couple linearly to a field, but this time we don't have a cutoff in the field, and this form factor of 1 over k is not square integrable. And this causes some technical challenges. For example, we had to introduce correlations between the particles and the field by means of the cross transform in the measure of condensation or coherence. Okay, so I have a few minutes left. And then I try to say a few words about mean field limits of many fermions. So one could also ask, if I now don't have bosons, but I have weakly correlated fermions, if this could lead to classical radiation. And together with Søren Petrat, we looked at the Nelson model, where one again couples, so to say, linearly to a field, but this time, to simplify the situation with an ultraviolet cutoff, we looked at a many fermion limit which is coupled to a semi-classical limit. And like we have seen in the talk of Chiara Zafirio and also in the talk of Niels Benedikter, if we look at initial states which are in a volume of order 1, then they have a velocity with scales like order n to the 1/3. And then one gets, by kind of the same reasoning, this semi-classical scaling where this epsilon n appears everywhere where h bar would appear in the equations. So this can be seen, so to say, as the quantum field analog to the models which were treated in a series of papers which Chiara described, for example, by Benedikter, Porter, and Schlein, where one has a pair interaction between the fermions. So what one can then do, one can reason similarly. So if we have a Slater determinant and we have a coherent state of radiation, and since we have a prefactor of n to the minus 2/3, we have to scale the coherent state accordingly. Then we can, in the coupling term of the Klein-Gordon equation, we assume that we can approximate the density by the mean density of the fermions. We can replace the quantum field, and then we obtain, so to say, the fermionic Schrödinger-Klein-Gordon equations, where each orbital of the Slater determinant satisfies a Schrödinger equation where one couples to the Klein-Gordon field, and the Klein-Gordon field as a source term has the mean density of the electrons. And also in these equations, one still retains this semi-classical structure. And what we learned from this work of Benedikter, Porter, and Schlein was the importance of an initial semi-classical structure which one has to assume and to propagate. And now, since I'm running out of time, I maybe just shortly phrase the results. So if one initially is in a Slater determinant, which satisfies these two orange conditions, where the first basically says that the momenta are kind of uniformly distributed, and the second says the density only varies on a scale of order 1, then one can show in terms of reduced density matrices that this structure and the coherent structure is preserved at later times. So I hope I could give a glance on the fact that weakly correlated particles can lead to the emergence of classical radiation. We derive these results by, like it's usually in the community, I would say, by a quantitative study of the correlations around the mean field dynamics, and usually, so to say, the interaction makes the problem difficult. And maybe as a small outlook, one could also ask, can we get a norm estimate for this kind of systems? And one can embed, so to say, the particle space also in a Fock space, and then also derive a Bogoliubov dynamics and higher order corrections. And on this we are currently working. And this goes in a similar way, like, for example, was described in the talk of Lea Bosman or at the poster of Søren Petrat. So maybe I just say 1 second about the literature. So classical behavior also appears in different limits, but since I'm now short on time, I maybe just want to point out that the closest works are this work of Marco Falconi, where he derives the Schrödinger-Klein-Gordon equations from the Nelson model with ultraviolet cutoff by Fock space method for many bosons, and the work by Amari and Falconi, where they treat the renormalized Nelson model by means of the Wigner measure approach. So this is all I wanted to say, and thank you very much.
Thank you very much. Are there any questions or comments? So one natural question, I guess, would be, what about Pauli Fierz for fermions? That might be physically the most relevant model.
I mean, that's what I, of course, have in my head. One big obstacle there is if one wants to do Pauli Fierz for fermions, and in the end one also wants to take a limit for the cutoff, then one has kind of similar problems, like if one wants to derive, for example, the Hartree-Fock equations with, so to say, with Coulomb interaction. But this, of course, the goal, I would say, in terms of fermions.
Thank you. Any other questions or comments? Online? No? Then let's thank Nikolai again. So this closes the session. Let me maybe just repeat the comment Stefan already made yesterday, that unfortunately we could not give everybody who wanted the opportunity to speak here. In fact, we had really many very interesting sort of suggestions for contributions, and many people who could not speak actually have prepared a poster instead, so I encourage you to actually spend time and have a look at these posters. Thank you.